Test, test, test.
Great. I can hear you and see you.
Oh, great. Thanks.
I'll be your tech support for today.
Thanks, Ryan.
Yep. So I got it. We're streaming on YouTube, and I'm recording a copy as well. And I'll keep an eye out for keeping people muted, videos off during presentations. And if you need any other support, just let me know.
Okay, thank you. And maybe we can just show the first slide.
Yeah, go for it.
Up there.
And then you're also a co-host, so you should be able to mute and turn people's video off as well in case anything happens.
Oh, okay. Good to know. So is Mary here?
I'm here.
Oh, great. So we will run from your computer or from Ryan's? I guess from Ryan's.
Yeah, I don't have the PowerPoint. You have it, Hanli.
Okay, so it will be me who will run the slides, or Ryan, that's you. Either way, it's fine with me.
Yeah, I don't think I received a copy of them, but if you want me to run it and want to send them to me, I can do it. Or if you just want to do it from your computer.
Oh, I can do it. I think I dropped it in the what's it called, the Google Drive or something. But I can, let me get it and we'll run from here.
I'd prefer we do it from our computers so we have the mouse to guide everybody.
Okay. So do you see it? If you don't see it in the drop, I mean the Google Drive, I can send again directly to you.
Yeah, well, like somebody said,
I'm a speaker. I was just saying that I'd like the speakers to be able to present.
Oh, okay. All right, good.
If that's possible.
Yes, that's
okay. So, Hanli, do you want me to be the presenter then, I'll go ahead and do it. So I just need to find the Google Drive real quick.
Okay. Thanks. Well, I think we're at 1 o'clock. So so welcome to this CESM Working Group session, cross working group session on Cima, and stands for System for Integrated Modeling of the Atmosphere. Hopefully we'll get that first slide with that logo soon from Mary. And my name is Hanli Liu. I'm from the High Altitude Observatory of NCAR. I'm the Geospace co-lead for Cima and also the session chair. And the agenda page will come up soon, and that will list all the leads. We have the chemistry co-leads, Mary Barth here with me, and also I think Bill. Yes, thanks, Mary. Let's go to the first or the second slide, the agenda page. Yes, and Bill Skamrock is our weather co-leads. I think I saw his name there. And also our climate co-leads is Andrew Gettleman. He's you might have heard from him about Cima in the previous CESM workshops. Obviously, he found a better place to be today. And also we have our software engineer project manager, Jordan Powers. And the project started, I think, more than 2 years ago. Since that time, especially since the Cima workshop last summer, many great progress have been made, both in software infrastructure and development, and also science development applications. And in today's session, we'll hear a lot of great things, the progress about those development. So Mary will be the first to give an overview and update on the Cima, like the status report of Cima. And then we'll have 5 talks going into more detailed discussions of each subject area. So as in the other virtual sessions, I will make sure that everyone's muted during the talk, and you can type in your questions in chat box, and we'll get to that at the end of the talk. Each talk is 15 minutes, and I will let the speaker know when you have 3 minutes left. So I think without further ado, Mary, go ahead.
Okay, so hello, everyone. So I will give an introduction to the System for Integrated Modeling of the Atmosphere, or SIMA. And I want to start with this pair of diagrams. So on the left side, you see a diagram that shows the atmospheric modeling ecosystem at NCAR currently, or a few years ago, but currently. And what we're doing is showing what models we use for different applications at different time scales, which is shown at the bottom, and different spatial scales shown on the left axis. And so, for climate modeling, we use the CESM and CAM model. We use Wakamex and Wakamex to get up into the upper atmosphere. But you can go down in scale, and that's when we might want to use the model for prediction across scales to look at synoptic and mesoscale weather systems. Same with the weather research forecast model, looking more at the regional scale and smaller scales. And then focusing more at cloud scales and turbulence, we have cloud models and we have large eddy simulations. And then, of course, we also have process models that are locally centered. And our vision for SIMA is to take this modeling ecosystem and move it to what we see on the right. And so we have one modeling infrastructure for this whole range of scales, from local scales to regional scales to global scales. So the SIMA vision it's an effort to unify NCAR-based community atmospheric modeling across the weather, climate, chemistry, and geospace sciences. And some of you may have attended the SIMA community workshop that was sponsored by NSF last summer. We spent a couple days thinking about SIMA, what we envisioned SIMA to be. You might remember the exercise of picking your headlines of what we might have accomplished in 5 years or so. And along with that, in the SIMA workshop, we talked about some important model requirements, and some of those are listed over here on the bottom right. So we went through that exercise, and we revised and updated the SIMA vision statement. And so some of the things that came from that is what's listed here. So we want a configurable system, not a single model. We want atmospheric models within an Earth system model like CESM. We want to have a minimal set of interoperable components. That means physics parameterizations, chemistry, upper atmosphere parameterizations, as well as dynamical cores. And we have we really want to have a common infrastructure and methods. And so that means we can share and extend our diagnostics among the different scales. But it also means that we're reducing duplication of effort. But even more important, we can take us, the community, forward and address some frontier applications. For example, looking at extreme weather events in the climate scenarios. So let's talk about SIMA and CESM. So just want to be clear with this community. So SIMA is a way to configure the atmosphere model for CESM. And SIMA also allows for new use cases beyond climate, such as urban or regional chemistry, weather forecasting, or geospace applications. This CESM Atmospheric Working Group will decide the configuration of the atmosphere model that it will use for the climate applications. Okay, so that's really important to remember. It's going to be controlled by the Atmosphere Working Group for the climate simulations. Let's think of it schematically. So shown here in the green border around the outside is CESM. And on the right, you can see the model components that are in CESM and the coupler. And then on the left, we zoomed in as to what SIMA is. And let's go ahead and zoom into SIMA. and think about, what does it mean? And so I'm going to go through a number of slides showing possible CIMA configurations. So CIMA climate, or maybe, CAM7, what is used for traditional climate studies, could be configured like this: CAM physics with aerosols coupled with the spectral element dynamical core as part of the Earth system model. For polar applications, we might want to zoom into the Arctic or Antarctic regions. And so you could have the same physics and aerosol parameterizations, but use the regional refinement capabilities of the SE dynamical core. And that's true with chemistry too, and this is already in existence. We call this Musica version 0, where we're able to do regional refinement over a particular region of the globe and look at regional air quality in the global context. For geospace, we could have similar configuration, but add in the geospace parameterizations for the upper atmosphere. And in some cases for like space weather, include data simulation. And then when you come to weather applications, you can switch dynamical cores to the non-hydrostatic dynamical core that MPAS has. And you could switch it to a physics scheme that's appropriate for mesoscale processes like the WRF and MPAS physics schemes. And again, you can also include data simulation. And then, the benefit is that it's now an Earth system model, and we can couple this with the ocean model to look at science topics like tropical convection and tropical cyclones. And we can add chemistry to that. And we can then zoom in and look at urban air quality in the global context, or we can look at the impact of convection on regional to global composition. And so I'm just kind of reiterating here that the chemistry will benefit both in terms of looking at urban and regional air quality with this new system without having to duplicate efforts among different models. So here's the status of CIMA. We now have a website, cima.ucar.edu. If you go there, you'll find this front page shown here on the right. And so that's up, and you can learn more about what's going on at that website. And so just as an update on what we've been doing last fall, 2020, we released the Musica version 0 as a comp set of CESM. And so that's now available for the community to use. Last year, we also spent a bunch of time working on a physics suite from the WRF and MPAS models to become compliant with the Common Community Physics Package, CCPP. And so that physics suite is ready to move forward when it's ready, when we're ready to make the connections. This year, we've been working on SIMA version 1. And one of the first things that we did was hire a project manager to oversee the software engineering efforts. And that project manager is Jordan Powers. He does that about a quarter of his time. And then we've been designing and developing new SIMA version 1 configurations. And so let me describe those a little bit further, and you're going to hear more about those more in detail in these upcoming talks. And so we picked a number of science questions and target configurations to go after, and I'll just go through these one by one. So for coupled weather, the goal was to have the MPAS dynamical core with a regionally refined grid going from 15 kilometers global down to 3 kilometers over a region, such as shown there on the right. And again, the benefit would be coupling this to the ocean model so we can look at this tropical weather. Moving to air pollution or air quality, we also put in a lofty goal to have the MPAS grid mesh, but now focused a little bit more over Asia, looking at both the emissions in the region, but also the impact of convection on the upper troposphere, and doing this as part of the ACLIP field campaign. Moving onwards, the science question of hydrological climate extremes. There's sort of two parts to this. One where we do regional refinement over particular regions like the US and South America. And those are shown here. You'll hear more about the South America simulations in a few minutes. And then the second part is part of a bigger project called Earthworks, where it'll be looking at the global uniform 4-kilometer grid mesh with CAM and MPAS. To address space weather, Hanli and collaborators are looking at a configuration where you have 25-kilometer grid spacing over the globe, doing both the atmosphere to the ionosphere with the geospace models. And then there's a polar prediction where there's regional refinement going down to 25 kilometers over the Arctic, coupled with Greenland, and over the Antarctic, both in uncoupled and coupled scenarios. And again, you'll hear about this more in a few minutes. So I'm just going to sum this up so we can hear more about those particular configurations. So just to remind you that this is what we've been working on this past year, but we've also been starting some planning for next year, so for SIMA version 2. And we'll hear more about that after these next set of talks and at the beginning of the discussion period. So with that, and I'll take any clarifying questions, otherwise we can move on.
Thank you, Mary. Gökhan, go ahead.
Yeah, I missed the beginning of the presentation, Mary, but at the end you were showing regional refinement versions within CIMA version 1.0. And for example, for the South American grid, you have both SE core and MPAS dynamical core. And it looks like you have the same thing for Himalayan Himalayan regional refinement. Why is the CIMA project rather pursuing duplicate sort of configurations with different dynamical cores?
So Gökhan, they're actually not duplicate. They're going in, let's go here. The MPAS grids are refining even further to the non-hydrostatic grid spacings. So, I mean, I can go into here, right, with the chemistry one. So this is going from a 15-kilometer outer grid to a 3-kilometer grid spacing in the middle so that we can explicitly represent convection in this region.
Okay.
So yeah, it's not a repeat. It's an enhancement.
And also, Gökhan, I should add that the CIMA is not a single model. It's a single framework. So different dicores could be used, as Mary just showed.
Right. Thank you for repeating that, because that's what I'm trying to get the message across. We don't have a single modeling framework at NCAR, but we have a framework for a combination of models. I think it's important to convey that message.
So that is funny. I should have ended with the slides that I started with, because that is exactly where I started, that it is an infrastructure. It's a system, not a
single model.
Not a single model. That's right. Any other clarifying questions?
No?
Okay.
Okay. Thank you, Mary, again. So now let's go to our next talk. It's by Kevin Fan from HAO, NCAR HAO, and talking about Wakamex coupling with Gamera. Kevin, are you there?
Yep. Let me share my screen. All right. Can you see it okay?
Yes.
Okay. So I'll be talking a little bit about Wakamex coupling with Gamera. I'll also briefly describe what is Gamera. So I'm Kevin Pham at NCAR High Altitude Observatory. So why do we really want to couple Wakamex with Gamera? And part of the reason is that the Wakamex development is ongoing. It's the latest and greatest, and it's significantly better than the old Tide GCM model that it replaced. And in the geospace community, we're still using Tide GCM for a lot of things, and it's about time that we start moving to something better. So in the Wakamex development side, there's the new spectral elements dicore. I think Peter will talk about that later. And there's also the new regridding scheme, which is very important for moving back and forth between the different grids in geospace. You have the geographic grid, you have magnetic grid, and so on. So there are a lot of different grids, and an efficient regridding scheme is very important for that. And so in coupling between Wakamex and Gamera, Gamera is the grid agnostic MHD for extended applications. And it's a newly developed magnetosphere MHD code that was designed with exascale computing in mind. It replaced what was known as the LFM magnetosphere model that was built, approximately 40 to 50 years ago. And so having a new model, a new magnetosphere model is very good. And so Wakamex and Gamera coupling is also part of the multi-scale atmosphere geospace environment, or the MAGE coupled model. And this MAGE model is part of the Center for Geospace Stories, which is one of the NASA Drive Science Centers, with the PI being Slava Merkin over at APL. So currently, the current work for Wakamex and Gamera coupling is just a single one-way coupling from Gamera to Wakamex. And so this is being tested right now, where Gamera is providing the electric potential and energetic particle precipitation in the high latitudes for Wakamex. And then Wakamex, and this is specified at a 1-minute cadence. We drove Wakamex one way using both the old FV dicore as well as the new SE dicore. And then this is compared to TiGCM. So I'll talk about this in a little bit. So why do we want to couple Wakamex to Gamera? So from the Gamera side, we want Wakamex because Wakamex is significantly better than TiGCM that it replaces. So why does Wakamex need Gamera? So normally, if you don't couple to a magnetosphere model, the high latitude driving for Wakamex is driven by an empirical model such as Helix or Weimer. In the MAGE coupled model, which is this diagram that you see down here, Gamera is coupled to, so Gamera, which is the global magnetosphere model that you see here, is coupled to a ring current model, and it's also coupled to an ionospheric electrodynamics model. So these three models are coupled together through MPI coupling. These three models are then coupled to TiGCM using a file exchange coupling. This becomes important in a little bit. So the future plan is to replace this coupled system, this TiGCM, with Wakamex in this coupled system. And so if you take a look at this middle diagram here, this becomes important. So the blue line here is the results from MAGE for the electric potential driving, and then the amount of heating into the into Wakamex or into the ionosphere is through this bottom panel here. So in the MAGE couple model, which is the blue line, you can see that as far as the electric potential, you see significantly more variability within the electric potential. Similarly, in the Joule heating, you can see that it has significantly more variability in the Joule heating. If you're using Weimer, the empirical model Weimer, you can see that everything is very averaged out, it's smooth, and you're missing a lot of dynamics for the input. So in the right side here, which is just a polar plot of the line plots that you see on the left, the right side here, you can see that from MAGE, which is this the top row here, you can see significantly more small scale features compared to the Weimer model, which is the bottom plot here. You can see in Weimer, it's very diffused and large. So replacing it with a dynamic magnetosphere model is a significant improvement. So currently in MAGE, we're using TiGCM. So let me play this movie. So the results that you see in the top panel here, in the top row here, the polar plots is the neutral density at 400 kilometers. You can see two satellites flying through, or virtual satellites, Champ and Grace. They're flying at about 400 kilometers or so. And every time they fly through, you can see that occasionally you see these waves that are propagating out from the pole due to the high latitude heating from Gamera. And so occasionally these satellites will cross these waves. And so if you heat in the wrong place, you will generate these waves with the wrong amplitude and velocity. And then the satellites, the spacecraft, will not measure them at the right time. you can see a comparison between the MAGE neutral density and the spacecraft neutral density in the bottom line plot here. And you can see that a lot of these variability, a lot of these enhancements and spikes that you see, we're capturing. And a lot of these are actually these waves that the spacecraft are flying through. So we're doing a pretty good job using a couple model in order to get what these enhancements and spikes are. Let's see. So in the one-way coupling to Wakamex, we run MAGE separately, and then we take the results from MAGE, and then we pass that to the high latitude Wakamex, so the pole region of Wakamex, in both the northern hemisphere and the southern hemisphere. And so the development of Wakamex SC is pretty significant because you don't have singularities at the pole where you're putting your convection patterns. If you have to do some sort of filtering at the pole singularity, you start losing a lot of information that we're inputting. And so having a high resolution and exascale ready high latitude driving into Wakamex SC is very important. And so this is a comparison between this is a spectral analysis between the three different models. So you have TIGCM results, which is the dotted line. You have Wakamex finite volume dicore, which is the dashed line. And then you have the solid line is the Wakamex SE. The altitude changes between lower altitude and the bottom row here to higher altitude in the top row here. And then you have, this is the northern hemisphere at 65 degrees latitude. You're near the equator, and then 65 degrees in the southern hemisphere on the right here. So you can see that so you have wave number in the x-axis, and then it's wave power for the y-axis. And you can see that when you get to the higher wave number, TIGCM starts losing a lot of power at the high wave number, especially when you're at the northern and southern hemispheres. You can see that there's a large drop off. In the equator, you can see there's a much larger difference between the three models. Wakamex FV has filtering at the high latitudes. And so since you have filtering near the pole, that also contributes to losing a lot of the power at the higher wave number because you're filtering a lot of them out. With the SE dicore, you're able to capture and maintain a lot of the wave power at the higher wave numbers. And you're able to capture a lot of that just throughout the globally in both the higher latitudes as well as the equator. So if we can do a comparison of the temperature variation, the left panel here is Wakamex FV, the middle panel is Wakamex SC, and TIGCM is on the right. So the TIGCM is able to capture a lot of the large scale structure everywhere. It uses a ring average filtering for the pole singularity. However, in the Wakamex FV here, you're missing a lot of the large scale structures at the pole due to the artifact at the pole, but you're able to capture some of the smaller scale structures that you're missing in TIGCM. So that's due to the underlying Wakamex rather than the FV. In Wakamex SE, you're able to capture both the large scale structures that you're getting in TIGCM, as well as a lot of the small scale structures you see significantly more. And one thing to note is that the driving for all three of these is exactly the same. It's the same Gamera driving for all three. And you can see that the Wakamex SE results and distribution is significantly better. And so to put all of this into context or into numbers, how do we quantify the model performance? So you get something like this table here. The RMSE, the root mean square error, is the left set of numbers, and then the R squared is the right set of numbers. So we split the event into three parts. You have a quiet part where not a whole lot is happening. You have a main phase of a solar storm, a geomagnetic storm. You have the recovery phase, and then just taking everything as a single number. So the whole run as the whole event as a single number. So if you're using Weimer as a high latitude driving, so for RMSE, the smaller number, the better. With Weimer, during quiet time between Weimer, MAGE or TIGCM, and the Wakamex SE one way, you can see that during the quiet time, they're pretty much about the same throughout. However, in the Wakamex SE, we're actually getting significantly better RMSE. For the main phase of the storm, Weimer doesn't do a very good job. You get a big improvement moving to a coupled model MAGE, but then you do get some improvement moving to Wakamex SE. So you get further improvement going to Wakamex SE. However, if you go to GRACE, at the GRACE spacecraft, you go from Wakamex SE isn't doing that much better than Weimar for the main phase of the storm. But if you move to the recovery phase, again, you get significantly better. This might have to do with the way that we're coupling. You get two-way coupling in MAGE, but you don't necessarily have two-way coupling in Wakamex. And so during the main phase of the storm at the GRACE altitude here, that two-way coupling might become a little bit more important. And so once we two-way couple Wakamex SE, we should see significant improvement here. R squared, if you're closer to 1, it's better. And this captures how the morphology, how well you capture the morphology between the spacecraft measurements as well as the model measurements. So in Weimar, for a quiet period, where all the models are doing pretty well, Wakamex SE seems to not capture the quiet period that well. This has to do with the fact that Wakamex SE is capturing too much variability that is not seen in the data. However, in the main phase, you can see that going from 0.3 to 0.5, you see significant improvement going from a coupled dynamic magnetosphere model. Going from an empirical magnetosphere model to a coupled magnetosphere model, you see significant improvement. And then similarly in the recovery phase, you see a significant improvement. So when you take everything together, then going from using Weimar to Wakamex SE, you see a very large difference in both the RMSE as well as the R squared. So currently in development and future works is that we're currently developing a higher resolution Wakamex in both the vertical
3 minutes.
component and then the horizontal component. One-way couple, we will one-way couple the high resolution Wakamex with the high resolution Gamera. So high resolution Gamera can run at 0.5 degree or even 1/4 degree for the high latitude. And then for Wakamex, you can go down to 6 kilometers. And then we're also currently developing the two-way couple Wakamex with Gamera. And this would be replacing this will be using the file-based exchange that we're currently doing with TiGCM. So it should not be too difficult to couple. And so as a quick showcase, this is using Wakamex with 120 elements for the vertical, for the horizontal resolution, and then your vertical levels is 1/10 scale height. Normally we're using a 1/4 scale height as opposed to 1/10. So you can see that as you go from the stratosphere to the F region, 250 kilometers or so, we're getting significantly, we have a significant amount of structure, and we're able to maintain a significant amount of structure as we go to higher altitudes. And so the improvement to vertical scale as well as the horizontal resolution is important. So in summary, one-way driving of Wakamex SE performs significantly better than the two-way couple, or not significant, it performs better than the two-way couple TiGCM. And it's a significant improvement over using empirical models, especially just a standalone TiGCM. And it's able to capture a lot of the small scale structures that TiGCM is not able to do. This doesn't account for the lower atmosphere structures and features that Wakamex has that TiGCM doesn't have. And so that will be something to explore in the future. So once we do two-way couple, then we get a more self-consistent and high resolution driving from Wakamex in the high latitude. This should further improve the model performance for Wakamex when we move to two-way coupling, and then work to two-way couples ongoing. And then, like I mentioned, coupling to Wakamex enables the lower atmosphere to play a significant role in dynamically influencing all of geospace. Yeah, thank you.
Thanks, Kevin. We have maybe a time for one question. Okay, Steve, okay, I'll just read it. Why use a file-based exchange?
So we're using a file-based exchange because TiGCM is a very old code. So ripping apart the TiGCM MPI code to merge it with Gamera would be a significant undertaking, and it wouldn't necessarily provide that much of an improvement over file-based exchange. So the fastest way to get the coupling to work is using something like a file-based exchange. In the context of geospace, we typically our events are typically a couple of days at most, and so how fast TiGCM runs, even with the file-based exchange, the exchange itself is not a limiting factor.
Okay, quick question from Peter. Do we have observations to compare against for TKE spectra?
That's a good question. I honestly don't know. Do you know the answer to that, Hanli?
I don't think there's any very good because I mean at certain altitude, maybe in the MLT region, we have a bit more wind measurements there, either from ground-based or observation. I mean satellite. There we can get some information, but higher up it's very sparse. I don't think. Yeah. Okay, let's move on to the next one. Thanks, Kevin, again. And our next speaker is Patrick Callahan, and he's going to talk about variable mesh in CSM. Patrick?
Okay, thank you. You see my screen?
Yes.
Good. Okay, I want to start with a brief overview of the South American grids. Grids is plural here because we're actually talking about a family of refinement grids that encompass the South American continent, with resolutions ranging from 100 kilometers down to 6 kilometers. And for each horizontal grid, the high resolution region is aligned with an existing WRF grid shown in the figure on the right. And for each of these grids, there are two configurations. For the vertical, there's the default 32 levels, and there's a 70 level option, which maintains the same model top, but aligns the additional levels with those from WRF. In order to be consistent with the WRF simulations, strong nudging to error 5 outside the refinement region will be applied to impose boundary conditions. And because we're going to impose these boundary conditions, we weren't concerned about how quickly we would transition from the high resolution to the low resolution region. So we did as quickly as possible to reduce the overall number of grid points. And to facilitate future intercomparisons between different resolutions, the grid in the high resolution domain at each resolution is aligned such that at each element corresponds to exactly 4 elements at the next highest resolution. And I'll go into more details of why we said we tailored these grids to match WRF this way in a bit. So this work is part of the development of these grids as part of the CAM7 supplemental funding, and it overlaps with efforts in SIMA, Musica, and the NCAR Water Systems Group focus on South America. So the goal of this an essential goal of this project is to simplify and streamline the workflow for variable resolution grids. So researchers can focus on science questions rather than the modeling mechanics of how to set up and run with variable resolution grids. So a long version of the title for this talk is Variable Mesh CSM for South America as a test case for streamlining and simplifying the workflow and assessing the fidelity of the high resolution simulations with intercomparisons with convective resolving WRF results. So I'll give a brief summary of the current workflow and then talk about some pending improvements to that workflow, and then wrap up with talking about the problems that emerge at higher resolutions and what we're going to try and do to address them. So the current workflow, you create a grid, and then you run a series of scripts and programs to generate mapping, domain, and initial condition files. And then once those are done, you install the grid by basically copying them into a local repository. And then you go through a process of iteratively adjusting the configuration values until you get the model to run stably, and you end up in the it works phase. So it'll run at that point. So the current process is fairly smooth, and there have been no major problems reported with it. Most of the problems have to do with when the grid resolution gets pushed down to 3 kilometers. There's some difficulties that we have to overcome yet. And other than that, the only other problem was a user that didn't have access to the NCAR environment had some trouble getting the files that they needed to create their grids. So with Adam Harrington and John Truesdale, there's a number of resources we have available. There's a tutorial on creating and running the grids available somewhere online. The variable resolution tools and documentation are available in GitHub repository. We've created a high resolution variable resolution bulletin board for users that need support and help. And we are working on a high resolution variable resolution website it'll be available soon. It'll have we're hoping to have full documentation, tables of working configurations, meshes, and data sets available there, along with FAQs and links to additional help resources. So once you get the model running, there's usually additional steps that are needed to tune the model and to pre-process data sets that may be needed depending on your usage. Of these, you have to pre-process emissions data. And then if you're going to nudge the model, you have to pre-process the nudging data onto your new grid. And the resources for doing this are available as part of the Musica toolkit. And then once you get done, if you're going to have you need to validate your model, then you go through the process of land model spinning up the model and tuning for validation. And Cecile is heading up an effort to have documentation on giving guidance on how to do that. So of these, the pre-processing of the nudging data is the least simple and efficient in terms of time and disk resources. So the generating of the mapping domain files and the pre-processing of nudging data right now are the most time computational and storage. They require the most of that. So there's a couple of things that are coming soon that will simplify these steps. And the first is the new OPSI coupler will simplify the process of generating the mapping domain and initial condition files. And by simplify, we mean eliminate, because a lot of those things will not need to be done anymore. Inline regridding will simplify the process and eliminate the need to pre-process the nudging data. So there will be initially it's basically a set of 4 modules that will maintain and manage the processing paths between input and output grids. And the horizontal mapping module will also accommodate user requests for other computational methods for horizontal grids. For example, zonal means or spatially filtered values that can be used for scale selective nudging. Once the horizontal and vertical options have been validated, temporal map module is going to be added to manage the data time slices for higher order methods for managing the way time is interpolated in the nudging. An example would be a local diurnal fit. The current nudging values applied to a given time are retained by a linear interpolation between reanalysis time slices. And a paper that's in review from Nick Davis has showed that there are non-negligible errors introduced when the interval between these time slices is longer than 1 hour. And lastly here, each of the components will have a user template to accommodate installation and testing of new mapping options between model grids or for new data set grids that may emerge in the future. So hopefully this will be extensible and flexible for new applications. Some new nudging features will be added to further simplify the workflow. So using the refinement map from the grid editor can be used to impose or to define the boundary conditions. You can impose them independent of the interior nudging. And selective nudging with larger scale variability will also be available as well. So the ultimate goal for optimizing the workflow is to have it easy to use. So once a grid is created, the user can only have to spend a minimal amount of time getting the model running. So these improvements will greatly reduce the work at the generating of mapping, domain, and initial condition files. And the pre-processing of nudging data will be eliminated, and nudging will only require a modification of a name list to switch it on. So with the ease of use of high-resolution regional grids are becoming more common. And unfortunately, these high resolutions expose 2 fundamental problems that may produce biases that limit the realism of CSM at very high resolutions. CSM is a hydrostatic model, so when the grid resolution increases, this approximation breaks down and the non-hydrostatic effects become important. The other problem is the so-called gray zone problem. where at resolutions below about 10 kilometers, convection becomes partially resolved and the assumptions underlying the convective parameterizations break down. So this is a problem because ultimately we want a model that's easy to use, but we also want it to give realistic results. And that these problems lead us back to why the grid domain was chosen and configured the way it was. Shown here is the website for the South American Affinity group, and is part of the NCAR water systems focus on energy and water cycle of the South American region. It's a collaborative effort across NCAR and the international research community. And one of the main roles for NCAR is in development of a high resolution convective permitting modeling system for South America. And the members of this group have self-organized into a number of overarching research areas shown here on the left. But and one of the main things is that there are 3 one-year-long simulations that are underway for each phase of the ENSO. And so the results of these simulations will provide a great resource for assessing the CSM results across horizontal resolutions. And there's an observational component to this as well. So observational data for the region will be used to evaluate the results of both WRF and CSM. And they're working down the road. There will eventually be 20-year-long simulations for this region. So to take advantage of these WRF simulations, Richard Neal, Julio Bachmeister, and Kristen Rasmussen, and myself have an NSC allocation to carry out a series of one-year simulations for the refined regions over South America, aligned with the 4-kilometer grid. And so there will be 4 resolutions available, and we'll run it for 3 phases of ENSO and for 2 vertical resolutions. So all of the experiments that we will run will consist of basically a set of simulations for the 4 horizontal resolutions, 100 down to 6 kilometers. A set of baseline 1-year simulations for each phase of ENSO will be run, one with the deep convection on, one with it off, and those will be run with the 70 level vertical option. And in addition to those, there'll be a series of 1-year simulations for selected ENSO phases with deep convection on off, running with the 32 level option. We'll try some different alternate reference surfaces for damping, and maybe some alternate spectral damping applications. And so, oh, okay, thank you. So the alignment of the spectral elements of these grids will allow for a high order partitioning of the 4-kilometer WRF results into resolved and subgrid values at each resolution, where the resolved values nominally represent the results we expect to obtain from lower resolution simulations. And ideally, the parameterizations representing the subgrid variability would reproduce the tendencies of recovery evolution of the resolved scales. So, and lastly, to address the hydrostatic limitations, additional non-hydrostatic correction terms will be included and evaluated in comparisons with WRF results. So for non-hydrostatic terms, other than those associated with vertical accelerations relative to the model surfaces or movements of the model surfaces, they all can be included in the vertical momentum equation without having to modify the current prognostic equations. The result is a differential constraint that can be readily solved via fixed point iteration and with the associated contributions distributed throughout the governing equations. So these South American variable resolution simulations and the contemporaneous high resolution WRF simulations will provide a valuable resource for the development and improvement of parameterizations. And down in the future, it was initially, we tried to have a 3-kilometer grid in the set, but it was not able to pass a number of the initial tests, so it had to be excluded. So we'll, once those problems get resolved, there'll be a 3-kilometer option added to this family of grids. And then down the road, there will also be non-hydrostatic impasse simulations that we can also do intercomparisons with as well. And thank you.
Thanks, Patrick. Any questions? Okay. If not, we'll move on to the next one. Thanks, Patrick, again. And so our next talk is by Adam Harrington from NCAR CGD.
Sorry, I was looking for the unmute button. Okay. All right.
Yep.
That was an excellent talk from Patrick, and definitely makes you appreciate all the steps required in generating a new grid. And so this talk is going to be entirely focused on the it works phase, and just talking about the science. So it's a nice segue. I'm talking about Cima polar. And this is a picture of one of the polar grids, a nice little visualization. You can see the grid lines and the precipitation rates. Anyways, I'd like to also acknowledge people who've helped me along the way: Bill Lipscomb, Andrew Gettleman, Marcus Laverstrom, Peter Lewitson with his name spelled wrong, Kate Thayer and Calder, and Bill Sachs. So let's get started. I'm just going to talk about some science results from the polar grids. And so this is the two Arctic grids here. All the polar grids are using the spectral element dicore. So the Arctic grid is this, we refine the top panel of the cube sphere to 1/4 degree and 1 degree outside of that. And the Arctic grist grid is further refining the Greenland ice sheet to 1/8 degree. And so these two are available to run right now in CSM 2.2 with these grid aliases. And then I'm going to be talking about, I'm coupling this Arctic grid with the pop ocean right now. And so I'll give you a little status update on that. And if I have time, some preliminary results from this newest polar grid, the Antarctica grid. So in order to evaluate a variable resolution grid, we need to know it's good to have low resolution reference solutions. And a tangential science interest of mine that I think is fascinating is for your sort of typical GCM resolutions, these 1 degree grids. So this is the finite volume 2 degree, finite volume 1 degree, CAMSE C-SLAM 1 degree, and the same but with a coarser resolution physics than the dynamics. You can see that the Greenland ice sheet is something that's sort of marginally resolved in GCMs. And so I always like to understand if we're going to be moving out of lat long world into quasi-uniform unstructured grid world, are we losing sort of the higher resolution representation of Greenland that we had benefited from these lat long grids? So this is there was a talk earlier about how the polar issues, the polar singularity issues in these Wakamex high atmosphere runs. And so yes, there is a polar filter that will oppose the formation of scales at these grid scales. But you know, despite that, there may still be some improvements in the representation of the Greenland ice sheet. So here is what the average grid spacing over the Greenland ice sheet looks like for all 6 of these grids. And so this green one here is the CAMSE NE30PG3, and so it's 1 degree average grid spacing over Greenland, 111 kilometers. Here's the finite volume 1 degree where you benefit from that latitude longitude grid, and it's closer to 60 kilometers. Finite volume 2 degree is not that much more coarse than the NE30PG3, interesting enough. And PG2 is a little farther out here. The Arctic and the Arctic grist grids are 27.8 kilometers and 14.3 kilometers respectively. So I did some 20-year simulations of 1979 and 1984 of all these 6 grids in CAM6. And what's shown here are the primary source and sink terms of the surface mass balance integrated over the entire Greenland ice sheet. The black line is a time series from RACMO, which does a very good job of reproducing the observations. And so for the purposes of this talk, that will be the truth. And so your integrated precipitation, your purple and your pink lines, which are the Arctic and Arctic GRIS, do very well compared to RACMO. The 20-year averages are over here in the circles. The CAM-SC grids precipitate too much. And the finite volume dicore grids are somewhere in between. The runoff term, so it's snow plus ice melt, but it's also runoff from rain precipitation that just ran off in a river. And so, but there's the runoff terms, the finite volume and the variable resolutions actually perform very similarly, and that is skillfully compared to RACMO. Whereas the CAM-SC grids you see are down here, and so it tends to produce too much runoff. And so to look at this a little closer by sectors of the Greenland ice sheet, and so these are these Wally basins. The ones that I want to focus on are 3 and 4, which are southeast Greenland, which get most of the precipitation, are in these regions. 7 and 8 get quite a bit too. But so this is 3 or 4 here, and this is the integrated precipitation over that basin. And your RACMO and your purple and your pink, so your VariRes, are doing quite well. Again, the higher resolution, you tend to get smaller integrated precipitation. FV, I should say CAM-SC, it has too much precipitation in these regions, and then finite volume is somewhere in between. And so, you know, the takeaway is that all 1 degree grids overproduce precipitation, and that SC is worse than FV. And the VariRes reduces the bias. And this is probably due to more realistic orographic precipitation. So once you start producing a more realistic precipitation pattern that dumps out snow right at the coastal margins, instead of letting letting the moisture propagate further inland, the net effect is you actually have less. The better you resolve the orographic precipitation, the less precipitation you actually have. And this bottom bar plot is snow plus ice melt, so it's not runoff. It's purely how are we resolving the melt processes. And this is interesting because in 3 or 4, for example, the finite volume grids do just as well in this metric as the higher resolution grids, and CAM-SC sticks out as not doing all that well. A lot of this has to do with, we have a great downscaling for computing. I'm sorry, it's not even a downscaling. We use elevation classes to compute the SMB on the CLM grid. And in those elevation classes contains real information about the elevation area relationships of the actual Greenland ice sheet that we can't resolve. And so the elevation classes do an excellent job of really helping out at coarser resolutions to help you produce a realistic melt rate. But it has limitations in that if your resolution is too coarse, you can't take advantage of it as much. So one thing I wanted to test was, so this is the CAM-SC topography over Greenland, and it's very blocky. And this is the finite volume topography over Greenland. And what I wanted to test is does this blockiness contribute to the poorer skill of CAM-SC? So I tried to project this topography onto the finite volume grid, and so you get this laughable looking blocky world here that I don't know I'd ever be able to get past peer review, but that's the joy of giving a talk. And so I've ran that out from 1984 to 1998, and that's given in the red bars here. Again, this is integrated precipitation over Greenland, integrated melt. And you can see that the red bar more closely matches the light blue, which is finite volume 1 degree, than it does the light greens in all cases. And so it indicates that the blockiness of CAM-SC alone is not necessarily responsible for it, but rather, well, before I jump the page, you know, both of these, CAMFV has obviously terrain following coordinate. And so this bottom boundary condition may be very sloppy, but because there's grid cells, multiple grid cells in each one of these steps, the actual terrain following coordinate can kind of smooth out over that. And that's apparent if you just look at the surface pressure differences between a run with this regular topography and the one with the blocky topography. And so that's given here as the surface pressure differences. And you don't see any of the sort of fine scale features resembling the blocky topography in the surface pressure. And so ultimately, you know, I think that this suggests that the degradation of sort of the orographic precipitation and the CAMSC grids is not necessarily coarser topography, but just a lack of the dynamical resolution to resolve these fine scale flow features. And so in this situation, as much as I hate to say it, the lat long grid performs better than CAMSC for producing precipitation over Greenland. So that has nothing to do with variable resolution grids, but it's an interesting question. And anyways, so going back to variable resolution, so here's a nice pretty snapshot of the Arctic grist grid. I got a nice storm, you know, dumping out precipitation at the southeast coast with some vertical exaggeration to show that orographic precipitation. And so the sort of variable resolution really gives you that realistic orographic precipitation. It's hard to deny that that is certainly one characteristic of these variable resolution grids. Another way I decided to look at the storms is I used tempest extremes, and then I used a compositor to composite what the synoptic storms look like for northward of 45 degree north, which is where the refinement transition begins for the Arctic grid. And so here's just a nice composite of what all the storms look like in January, for example. You get the nice comma shape. And so if I do a PDF of all the precipitation rates for all the snapshots that make up this composite, so basically what are the precipitation PDFs of these storms look like for June, July, and August, and the red is the Arctic grid, and the black is ERA 5, and then the blue is the lower resolution solutions. And so clearly you benefit from producing more extreme precipitation that is more realistic in as much as ERA 5 is more realistic. Another question that I'm interested in is sort of these polar lows, which could be, you know, my understanding is there's a strong interaction of the surface winds and sea ice and open ocean surface fluxes that can contribute to the generation and the genesis of these storms. And so that's one research question that we're interested in, coupling this Arctic grid to the pop ocean. And so I'm going to give
2.5 minutes.
That's okay. And so here's what the status is of me coupling the Arctic grid to the ocean. Well, when I started out of the box naively, I ran it for way too long. This configuration is way too warm. This is the Cima control, PI control. And so I had to go to retuning. The VAR-res tuning approach that I took is you tune a 1 degree model, but you use the variable resolution physics time step. Most of the domain is in the coarse region. And the only difference in variable resolution versus uniform resolution at 1 degree in the coarse regions is the physics time step. So that's primarily the thing that's really altering your climate and that you need to tune for. So I try to get a reasonable spatial patterns of shortwave cloud forcing and get a good rest on. So I got there. So how do I initialize these runs? So this is this black line is the long CMIP 6 PI control for CSM2, and you'll notice it warms over the control period. And you know, that may not be ideal, but that is what occurs. And then these are the JGBG spin-up legs from Marcus's work, where he actually spun up the entire coupled system, including CESM, to be in equilibrium. And so the ice sheet's internal temperature profiles are equilibrated out here at the end. And so this is where I wanted to branch off. And so I did so here with the new tuned BCOM set, and you can see it's cooling a little bit. That's obviously a lot better than warming. And this is the configuration we're working for. So there's a multi-century runs in the pipeline all the way out. We have a 5-member ensemble plan for 1970 to 2020. And hopefully we'll be running that within the next week. I don't have time to talk about this, but please look at Tree's poster, Tree Data and Jan Leonard's at the poster session later today. And also YouTube, search for YouTube VisLab Greenland, and you'll see a really cool visualization of the Greenland visualization that I showed snapshots from in this talk. So I'm gonna stop there and take questions.
Thanks, Adam. Maybe we'll address one of the questions. Julio, maybe you can go ahead and ask your question.
Adam, I was just wondering, downscaling to the CSM, to the CESM grid is not going to help produce the right upslope wind that you need to get the right precip. Is that right? You'd have to, I mean, it's going to help you partition things into the right phase, but it won't control the amount. Is that correct?
That's not something I thought about before, but that's true. The downscaling is between CLM and CESM only.
Right.
What comes to mind is similar. Okay, let's stop talking there, but let's talk more offline about that. It's an interesting idea.
All right.
Okay, there's another question, but Adam, maybe you can address that in the chat box, and we'll move on. And thanks, Adam. So our next talk is by Forrest Lacey, NCAR ACOM, regional simulation of chemistry with Musica.
Great, thank you. Just share my screen.
Good.
Okay, can everybody see that and hear me?
Yes.
Okay, great. So yeah, I was asked to give a talk about basically the initial results of chemistry using Musica and the Cima framework, and then also some of the chemical model developments that we have ongoing in NCAR and at ACOM. And this is work that I've done myself, but also with a large portion of the Musica team as well, particularly Becky Schwantes, who is now on that series in NOAA. So just a quick overview of what Musica is, because Mary talked about this at the beginning, but Musica is an infrastructure for looking at chemistry and aerosols and modeling the atmosphere, something that's easily configurable, so we can choose different packages or different chemistry and aerosol suites based on our science question of interest. And this is, the vision paper was in BAMS just about a year ago. And how this links to Cima is that this all fits within the Cima framework. So our modeling of the atmosphere fits within Cima, and then Musica is a larger expansion of that that's specifically a tool used to solve different science questions. And this is a model and framework that's under development both at many labs in NCAR and also with our community partners. And I'll touch on that kind of at the end if we have time. So the specific cases that I'm going to talk about today are Musica version 0, where this is the version of the code that's been released in CSM 2.2. And this uses the spectral element dicore, and particularly with regional refinement over CONUS. So we have a global 1-degree model that steps down by a factor of 8 to give us around 14-kilometer resolution over CONUS. And what we can kind of expect from this is at finer resolution, emissions and chemistry are going to be more accurately represented. And pollutants are then simulated at human exposure relevant scales. So we're able to model things like ambient air quality within a global model, something that's been challenging in the past. And this also includes all of the global feedbacks that we get when using CSM. And as an example of the science questions that we're starting to look at, and as our first case that we did, we wanted to see how model complexity impacted our air quality simulations. So for Musica version 0, we looked at 2 cases. One of them using the standard NE30 grid, which is a 1 degree cube sphere shown on the left. And then the second one is that 1 degree global grid with a factor of 8 regional refinement over CONUS shown on the right. In addition to resolution improvement, we also wanted to look at chemical complexity, because we know that at finer scales, our resolution for resolving chemistry is going to be different as well. So we took the standard CAM-CHEM Mozart TS1 mechanism, which is around 150 species. And then we also simulated with the Mozart TS2.1 mechanism, which has improved isoprene and terpene chemistry, impact, and also a high NOx, high and low NOx pathway for SOAs. So we're really impacting both PM and ozone formation. And I wanted to show kind of why we're looking at both horizontal scale and chemistry complexity. So if we're looking at the significance of resolution, one thing that I think we're all familiar with is that wildfires are becoming an important source of ambient air quality. And this is showing the rim fire from 2013, which was our simulation year, which at the time was the biggest fire in California. And you can see in the middle, which is the 1 degree model, we're really smoothing out emissions from that source over a much wider range. Whereas in the regional refined case, we're seeing the discrete fire points and then the impact of that. We can also see there's multiple fires going on throughout the Western US, which may not be as clear in the 1 degree model. And then if you look at the difference between those two, and the difference between those two shows that smoothing impact. And in terms of chemical mechanism importance, this is being shown here. These are now both the regional refined cases with the TS1 and the TS2.1 mechanism. And it's important here to focus on the difference plot. You're seeing that we're getting differences of up to 30 ppb, especially near populated areas. So there's the outflow from Los Angeles and in Southern California. We're getting large differences depending on what time of day and how the emissions are coming out of the city. So it's really important that chemical mechanism or chemical complexity also plays a role in air quality. So these are the kind of the takeaway results from the initial simulations with Musica version 0. And these are in papers that both Becky and myself have in preparation and planning to submit very soon. And in general, the results show that changes due to shifts in resolution are at least in the same order of magnitude as changes in chemical complexity. And this is especially relevant as we move to higher resolution. So here I can kind of explain that a little bit better here. Here we're seeing like a min and max change of around 40 ppb for changes in surface ozone as we shift from 1 degree to the regional refined case. Whereas we're getting between 15 to 5 changes in ppb as we shift just between the two chemical mechanisms. So they're not identical, but they're on the same order of magnitude. And this is very clear with PM 2.5 as well. So that was from the paper that Becky's preparing that compares specifically to a number of flight tracks. The one that I have is more health focused, and I'll discuss those results in the session tomorrow. But I did want to show some of just the model biases and how we've started to analyze those. So this is the shift in ozone bias and the shift in PM bias based on all available EPA AQS observations within both specific regions and seasons. And I think this is where it's really clear that both So the top is showing the shifts based on resolution improvements, and the bottom is showing shifts based on chemistry improvements or chemistry complexity. And I think this is where it becomes really clear that if you're looking at a specific area, there's often cases where chemical complexity is just as important as horizontal resolution. I did want to discuss as well the model independent chemistry module. So this is MICM, and this is basically a database and a solver that allows for easily changing a chemical mechanism. We were not able to use this for the Musica version 0 work, but I'll get to this in the conclusions. I think this is an important tool to help us answer some of the science questions that we're looking at in advance of complex global simulations. So what MICM is basically, it has a database of chemical information, and then it has some identifier about your host model or what your host model is expecting to have in a chemical mechanism. And then based on that, it configures the chemistry cafe, and then puts that into a chemical driver, and then puts that into the common physics framework, and in turn, the atmosphere model, be that whatever one we're using. And in addition to putting it within an atmosphere model, it also puts it into Music Box, which is basically MICM as a box model itself. So here you basically have all of these same input databases that you can access. And then you basically just pick and choose either by uploading a file or anything, either text or CSV that identifies what species and reactions you want to use. And then it takes that, configures it, and puts it into a box model. So these are basically the processes for using Music Box, which is available. I think it's still available via GitHub, or you can request it as well. All the information is here. But basically you load a mechanism, modify that mechanism as your based on your use case, and then modify any of the information about specific species. So if based on measurements, you have different Henry's law coefficients, and you want to see what happens if you change those within the chemical database, you can do that here. And then it allows you to run a box model and plot the model results and simply compare two mechanisms, which I think is important if you're talking about looking at chemical complexity and how that impacts air quality. This will allow you to run a number of different cases within a box model before implementing them into the computationally expensive Musica model. And this is kind of a demonstration of what we would expect to get. These results are actually from CamChem, but we would expect to have these within the box model of Music Box at some point. And basically you have the different mechanism name, the number of compounds, and then this would give you within a box model kind of the impacts on ozone for that mechanism, or PM2.5 or what have you. Other ongoing development, which I think has been touched on a little bit already as well, is the use of different dynamical cores within Musica. And this gets to Gokhan's question, why would we want to do that? Well, the reason we want to do that is to answer science questions about the impact of your assumptions about dynamics on ambient air quality. This may tell you or give you an uncertainty on ambient air quality based on your choice of dynamical core. We may have higher uncertainty in populated areas using the spectral element versus MPAS. So I think that the ability to have multiple dicores really allows us to get at some questions that are really difficult to answer moving forward. And in addition to the ongoing development, Patrick Callahan's done a lot of work on developing a user interface for generating grids. I've attached the wiki here, and these are just some of them that we're currently looking at or have been developed by users to look at specific science questions, be it the Asian monsoon, air quality over the Korean Peninsula, or the wildfires in Australia. So kind of conclusions that I want to discuss from this work are that Musica and Cima allow for the simplified evaluation of model complexity and how that impacts atmospheric state. And this is all within a single framework. And I think this has been highlighted a couple of times. It's important that this is a framework, it's not a model. The fact that this is within a single framework, though, allows the user to have some familiarity with it, and then makes it simpler to test things such as chemical mechanism or horizontal resolution or the impacts of dicor. Our initial experiments show that both horizontal scale and chemical complexity are of equal importance if we're looking at nonlinear species such as ozone and PM2.5. And I think it's a really nice segue to the fact that MICM and MusicBox are tools that can be aid in kind of exploring some of these questions before implementation into a 3D model. I think that's really powerful that we can test a chemical mechanism, see what results it has in a box model, and then directly have that same tool output the chemical mechanism within Musica. And as I mentioned, community support is present and needed to continue the development based on the various model components that we all have. And this is kind of an overview of the community involvement. It's all defined here on the website, but these are basically the model working groups that all have both partners within NCAR and within the university and national lab community. So I think with that, I'll end and take any questions if we have any time.
Thanks, Forrest. So I forgot to remind you of time. Sorry about that. So any question for Forrest? I have a quick, maybe naive question. Is MICM similar to the preprocessor we used before for Mozart?
So MICM is, so basically the type of preprocessor that you use that goes back to your model configurator. So like here, your host model characterization, that's where you would define what type of preprocessor you've been using in the model. So if it's KPP, this would identify that, and then it would tell it, it basically tells it to output a KPP file or whatever chemical processor you have. So it's very similar to that, but it's more flexible because it allows for output of multiple different chemical mechanism types.
Great, thanks. All right, let's move on to the next talk by Peter Lorenzen. It's Cima Dynamical Core.
Thank you, Hanli. So the official agenda has this correct title to my talk, but the Mary's slide had a different title, so apologies for this discrepancy for those of you who are paying very, very close attention. So this is basically a report from the factory floor of doing the plumbing for dynamical cores, in other words, hooking them up with physics packages, in this case, canned physics. There's a lot of people who have been contributing to this work. First of all, I'd like to thank the AMP software engineering group for all the code reviewing they've been doing and all the work we're doing, and Mariana Wertenstein and Jim Edwards for their Sema and CESM support. And then, in the last year or so, things have really started to move on the MPass integrations. I really would like to thank Miles Curry and Michael Duda for all the hard work that put in and all the discussions and spin up that Bill Skamrock has been providing to spin me up on the details of MPass. For the spectral element part of this talk, I'd like to thank Mark Taylor and Alexander Gruber, and as well as Francis Witt and Hanli Liu. And for the FFE project, I'd like to thank you, Christiana Debnowski and Lucas Harris. So it's a rather large group of people involved in this. So the Cima leads frequently slowed this slide here. I'm repeating it. So I'll basically be giving an update on these different dynamical cores that we're integrating into the CESM modeling system for Cima applications as well as CESM applications. So I'll just go through the dicores one by one. So FE3 was released with CSM 2.2. Apparently in the last year or so, there's been a lot of updates to the DICOR from GFDLs. We're pulling those into our modeling system. And then there's currently a funded proposal from NOAA to look at FE3 inside of CESM. So that proposal and our collaboration with Lucas Harris will help us to kind of finalize a quote unquote final configuration for the CSM dynamical core evaluation effort. With the spectral element dynamical core, there's also been some activity to accommodate new applications. So this here was added, I think, about a year ago or so ago, when we were doing Wacom simulations with spectral elements and comparing to finite volume. On the right-hand side, we see our reference simulation with 70-layer finite volume Wacom. On the left is spectral elements. And you see that we have a very strong degradation of the simulation of the QBO, which already at 70 layers with FV is not that great. But I had the suspicion for a long time that the vertical remapping was too diffusive and didn't have the time to code up stuff myself. So, but I knew that the GFDL had been working really hard on this. So we relatively easily ported over their vertical remapping codes that or algorithms that are much less diffusive, and we got a much better QBO simulation. But both FV and SC do need slightly higher vertical resolution for a good QBO simulation. So again, I think that the illustration of having several dynamical cores in Cima and gaining experiences with them have significant synergetic effects. Other changes that are not fully on the checked in on our quote unquote trunk, but are very close to being there is for a long time, Patrick Callahan and I have been observing noise with spectral elements over steep orography, and we later started to work with Mark Taylor on this, and he developed some simple modifications to the pressure gradient force and the damping of temperature, or the hyperviscosity damping of temperature, that really improved the simulations. I won't go into the details of the numerics here, but just show you the difference between the CSM 2.2 release of spectral elements on the left-hand side and spectral elements with these algorithmic modifications on the right. And I'm showing, a long average from an AMIP simulation. I'm showing the vertical velocity at 500 hectopascal. That's usually indicative of noise issues near steep topography. And when we introduce these changes, we get vertical velocities that are much more consistent with the other dynamical cores in Cima. As alluded to in earlier talks today and yesterday, there's been a lot of work in Wakamex in order to adapt the spectral element dynamical core for high top modeling, where you have species-dependent thermodynamics. Also, we've added operators to represent thermal conductivity and molecular viscosity inside the DICOR. So the DICOR takes care of the horizontal part, physics, the vertical parts. And we've had quite a few stability issues, so there has been changes to the sponge layer for high top applications. I just wanted to let people know that we tried to implement this in a very general way, both in terms of the composition of dry air, but also the moist aspects or moist components of air, such as cloud, liquid, ice, rain. And so we coded up a framework where you specify via the nameless which dry air species are active in your model. Here's the example from Wakamex, and here are the examples for CAM 4, 5, and 6. And that then tells subroutines in a common module what the heat capacity should be, gas constant, thermal conductivity, coefficients, and so on. So currently the spectral element DICOR and the CAM Wacom physics package now calls common routines to ensure thermodynamic consistency between physics and dynamics. And I hope we can make use of this infrastructure for other dynamical cores who wish to add this functionality to Cima. This plot here is already shown earlier today, so I'll just jump over that, but it's basically just showing the spectral element with all these new features active. So in the interest of time, I'll skip to the next slide. Now to the model for prediction across scales to enable fully non-hydrostatic dynamics within CAM or using CAM physics. So there's been a lot of interesting research here in figuring out how to do this consistency. So the basic consistency that we have to work with is that MPAS uses a z-based, a height-based vertical coordinate, whereas all the other dynamical cores and CAM physics use a pressure-based vertical coordinate. So we have to figure out how do we pass the discrete MPAS state, which is the modified potential temperature, velocity components, dry density of air, and dry mixing ratios. How do we pass that state into CAM physics that represents the atmospheric state via temperature, velocity components, pressure level, thickness, and specific or moist mixing ratios. So what I just said is described in the text down here. At a very minimum, we want mass conservation. So if we assume hydrostatic balance, that's pretty straightforward, because if you take the hydrostatic equation, integrate it over a layer, you can easily show that the pressure level thickness can be formulated in terms of MPAS prognostic variables, namely the dry density or the mixing ratio of whatever species are in air, and then dz that in MPAS stays constant. So that transformation is straightforward. A little detail here: MPAS, similarly to SE, similar to FE3, does have thermodynamic active water species that are not water vapors. They have all the condensates active, whereas CAM physics only takes into account the kinetic potential internal energy of water vapor. So we exclude the condensates in the calculation of the pressure level thickness. The next level of consistency can be formulated in terms of energy conservation, but basically when computing the energy, assuming now that MPAS is hydrostatic, so I'm not taking into account the non-hydrostatic effects at this point in the game, then we would like the energy computed using MPAS prognostic variables to be the same as that using CAM prognostic variables. There are a lot of devil in the detail here, but just to give you an idea of the kind of consistencies we've been deriving. So as I told you, the pressure level thickness is easy to compute. That means if we sum up pressure level thicknesses, we can get pressure at a certain half level, so in between levels, by computing a consistent top level pressure, which is not constant in MPAS. However, we have to be really careful when we compute the mid-level pressure. So we can't just take the arithmetic mean of the pressures. Sorry, it should have been a plus, not a minus here. Because that's not consistent with MPAS that defines the mid-levels in terms of the arithmetic mean of the height, not the pressure. Anyway, you can use the equation of state to compute what 1 over the pressure should be at the mid-level. And it similarly follows the Exner function expressions. So long story short, it means that if we use these formulas here, then when we compute the height on the CAM physics state, for which height is diagnostic, we get exactly the same height as is used in MPAS. And that then results in consistent energies when we're passing the state from dynamics to physics. So now to a much harder problem, namely the time evolution of energy in the model. So the CAM physics package was designed with energy conservation in mind. And the issue we're running into, you don't need to read all the text here, I'm going to tell you, but the issue we're running into is the CAM physics energy temporal evolution of energy. That formula here is different for what's used in MPAS, because here we are assuming that the model's top pressure is constant. MPAS has a constant Z formulations, and these two energy formulas are different. So the question is, what do we do? So in order to understand this energy flow a little better, one has to understand the time integration in CAM MPAS. So again, you don't need to read all the details, but it's illustrated in this pseudo algorithm on the left-hand side. So the first thing we do is we go into dynamics, immediately pass the state to physics. I just described how we do that. Then we run all the physics packages incrementally. And in CAM physics, the energy budget is closed if we assume that the pressure stays constant during physics updates, which of course is not true when water enters or leaves the atmosphere. So at the very end of physics, we have what we call DME adjust. DME adjust, we account for the water change in the column. We're not treating that energetically consistent, so we're letting the energy fixer fix that. Then we transform everything back to the dynamic state, run the die-core, start over again. So the part of this loop here shown with these light gray arrows here, that's what the energy fixer is fixing. So we need to have a consistent energy formula consistent with MPAS when we're fixing these energies. Otherwise, we end up not fixing the right thing, so to speak.
2.5 minutes.
So what we ended up doing is that we let physics do its own thing since it's internally consistent. And then we use the MPAS hydrostatic energy formula for this part of the time integration where we have the light gray arrows here. Also, since CAM physics was formulated in terms of constant pressure, we need to scale the temperature increments for constant volume. So they are scaled with this increment here. If you do that, then the energy increment associated with heating are consistent between these two energy formulas. So this should show you an importance of keeping, having consistency here is if I were to compute this moisture adjustment using the CAM physics formulas shown on the left-hand side here. This is a 1-year average of the energy tendency due to that adjustment. On the right-hand side here, I show exactly the same thing using the energy equation consistent with the MPAS dynamical core. They look similar, they should, but they're different in the details and in the average value that's written up here. But if we subtract the two from each other, you see that locally you can be a couple of watts off due to inconsistent energy formulas. So I think we've reached a first level of consistency in terms of that the energy fixer is doing the right thing. However, on the longer term, I'd still like to point out that there are still some inconsistency due to constant pressure, constant pressure physics and a constant volume dynamical core. It relates to the static energy that's used to update the physics increments. If you just do the CP over CV scaling, you do get the temperature increment right, but Z is a diagnostic in CAM physics, so it means that the Z levels actually do change in CAM physics, which is not the case for the MPAS dynamical core, so there's still an inconsistency there. And related to that, the top boundary condition in CAM needs some attention because that assumes constant pressure. Probably not a problem for low top modeling. So for high top modeling, Han Li tells me that the model top moves up and down by about 100 kilometers or so, which needs some attention so we get the correct boundary condition formulated. And again, I put these in light gray. We're still assuming hydrostatic energy formula. So obviously, if we go to non-hydrostatic scale, we could make it non-hydrostatic, which would mean the addition of the vertical velocity term, which is the only term missing in this formula, energy formula currently used. And then we're not including thermodynamically, rigorously including condensates in the energy on the physics side. That's also an inconsistency with spectral element FV3. So with that, I'll take questions.
Thank you, Peter. I saw a question from Mark with MPAS. Is CAM physics seeing the non-hydrostatic pressure from MPAS, or is it somehow only seeing the hydrostatic pressure?
I believe it's only seeing the hydrostatic pressure.
Okay. All right. So let's move on to the plan, future plans. And I'm going to share my screen here. Let's see how to do that. Okay, can you see my screen here?
Yeah, do you want to hit swap displays at the top? Because we can see your notes view.
Oh, yeah. Okay, let's see.
Perfect.
We're better now?
Yep.
Okay, good. All right, so let's back up a little bit. So yes, so we have seen all this grid development, and I think the plan, what we like to do is build upon this and go forward. So here are a few items on the top of our list. First thing we would like, the great achievements we've just seen, we would like to maybe engage the community and also let everyone use it. So the first item is to hopefully release the Cima V1 configuration this fall, and also have a tutorial and workshop also in the fall. And another important item is to create a Cima advisory panel or board to help guide further configuration development. And in this process, hopefully we'll bring the feedback from the community in the future development and configurations. And of course, the Cima science and infrastructure development is always central to this effort. And project this onto next year. So here are a few specific items we'd like to do on coordination, infrastructure, and science goals. So for the coordination, the software engineer project manager, it plays a key role in coordinating or communication between the co-leads and the software engineers, and also coordinating between or among the software engineers from different NCAR labs. So definitely we want to have a continued funding for that position. And also with the release, coming release of the model, we would like to have a Cima community liaison so that we can better know what are the needs from the community. And also mentioned earlier, the Cima advisory board and the liaison should be part of that board. For the infrastructure development, there are a few items already discussed. Yesterday, Julio in his talk, he mentioned the CCPP, the Common Community Physics Package. We like to bring that into Cima. And also common regrading, that's very important, as we have seen in this talks. There are a variety of different grids, SE, regional refinement, and MPAS, and also the geomagnetic grid. So it's very important to continue the work described in Patrick's talk. So for the chemistry development, Forrest already mentioned a few of them, and also the infrastructure for aerosol processing. That will be on our list for next year's development. And improvement of workflow. Again, Patrick in his talk gave a very good example of that. And so we want to improve the efficiency of pre-processing and also post-processing, analyzing all the results and the software tools for doing this. And for science goals, the configurations in this each of the subject areas, we already get quite a few simulations going, and maybe we'll have more. So definitely it will be very interesting to analyze all those results to gain new insights, and also maybe publish a lot of papers on that. And the development of Cima related diagnostics and also integration with observations. I think Louisa in her talk yesterday mentioned the work of Melody. I think that's a good example of that. And so that will continue with the Cima development. And for DA data simulation, as Mary showed in her talk, it's an important part of the Sema Vision. So So it's definitely what we like to work on. Currently, the data simulation on the CESM side and the climate and also geospace side, we're using Dart, but we'd like to explore maybe the first steps for also extend that to the weather applications. For geospace, we like to improve the ionosphere coupling. That what we have in mind is transition to a two-way communication or two-way coupling, and also maybe build on the kind of work described by Peter, work with AMPAS to develop a deep atmosphere dicor. So those are some of the things on our list. And I think we have 15 minutes left. We'll just open the floor for discussions, either the future plan or any other issues you want to bring up. These are the few items we have. You can, you have comments on this, just speak up, or you have other thoughts, also please go ahead. I cannot see anyone's hand right now. Mary, if you see anyone, you can call their names.
Yeah, no one's raising their hand yet.
Okay.
Thomas, you want to go ahead?
Hi, thank you. So I wonder about the base grid configuration you're using for the cube sphere grid. Obviously, it's excellent for covering the contiguous US domain, but it has these pesky nodes, and one of them is over the North Atlantic. I have read papers that were commenting on the danger of such nodes in the grid to actually generate spurious noise. And if they happen to be in the middle of the storm track, then you can actually generate weather numerically in that way. Has any thought been given to this? From the European perspective, where I'm coming from, this is potentially important.
Okay, so I'm not able to answer that. And I think there are some experts here that could. So Peter, did you want to say something or?
Sure. Yeah, so Adam and I have actually looked quite extensively at this with the spectral element dicor, where in like idealized aquaplanet simulations, we did see more variability at the element edges than in the interior of the element. So you have this spurious dependency on where you are in the element. And that's why we argued that you should not be calling the physics from these very anisotropic distributed points, but it should actually integrate over a more equal area grid cells and pass that to physics. And that's what we're doing with the spectral element CSLAM version. The only downside here is that we don't support this for variable resolution applications. However, DOE has a version of this physics grid that does support variable resolution applications. Does that answer your question, Thomas?
Yes, probably in part it does. I suppose it is exactly what you're saying, that the different area of the grid points have an influence on the dynamics. So if you are correcting for that, then it sounds the right way to go.
I'd like to emphasize that it's a physics dynamics coupling problem, not the dynamical core per se problem. It's how we couple them. At least that's what we found.
Okay.
But you're welcome.
Thank you. Judith, you want to ask your question?
Yeah, thank you so much. I think it's more of a comment. I'm not sure yet. Thanks so much. I think that was a super interesting question. I also really appreciated some of the details that came out in Peter Loritzen's talk about how difficult it actually is to use different vetted components and put them together. My question is about the resources. My understanding is this has been all done with very little resources. And my question is, how can the community get involved and contribute given resource limitations? How can the community help to get that off the ground and get it used?
So I guess I'll start, but the other CIMA leads can also chime in. So that's one of the reasons we're pushing to get to a CIMA version 1 set of configurations that can be released to the community. And then there's a reason for the community to use these configurations, but also then start giving feedback or create further developments. So that's where I see the community getting involved. And, you know, and hopefully that's right, that's soon, that's in the next few months. Yeah, Hunley or Bill, do you have any further comments?
I agree with what you said, and also I think there are already a lot of synergy. For example, for as Kevin talked in his presentation, there are a lot of synergy between, you know, CIMA effort with community efforts like the MAGE model or the NASA Drive Center. You know, this does have a high impact among the community participation and the users. I think those kind of activity, you know, will naturally be very helpful for promoting the status of CIMA. And also the co-funding of it. I mean, the you know, writing proposals to get additional resource for this development.
And I guess I want to make a further comment on the chemistry side of things, right? Because Musica version 0 has become mature. Forrest showed that after the initial configuration that he and Becky put together, that there are more applications going on. And that's not just within NCAR, but it's starting to happen outside of NCAR. But one of the other tactics we're taking is to try to create a community simulation that a number of people from the community can help analyze for their own research interests. And then someone was going to speak up.
Bill, you have something to say?
Jordan, did you say something?
Yeah, this is just a follow up on Hadley's point about proposals. And Judith, if there's a release with the release of CIMA v1 and a workshop and tutorial, once this gets in the hands of the community and they begin to use it, we certainly encourage them to work it into proposals where they plan to use it, pursue it, and evaluate it. So if NSF can see that it's popular and it has ground support, it'll recognize it as something that's worthy of funding, whether to individual investigators or perhaps to NCAR or other groups that want to develop parts of it and move it forward. Thanks.
Thank you. Any other comments about Judith's actually very good question about resources? Okay, so Gökhan, you have a question.
Yeah, mine is actually a little bit related to it. And I just wanted to sort of distinguish where and when community input can be considered. So far in your response and in the responses provided, I get the impression that actually the idea is to provide a framework or a simulation to the community after the fact, right? And then that's at least my impression, because you want the community engagement happening way before that. You want the essentially community to have something, a say in how that particular simulation was actually created. Is that the framework that community wants, rather than actually working on it and then putting it out for community and then hoping that community will get engaged. And another thing that, I mean, along the same lines, when Hanli showed the sort of the future structure of CIMA or proposed, I noticed that instead of a scientific steering committee, I don't know whether it was a mistake or not, there is actually a mention of advisory committee. And the two are quite different. And if there is a scientific committee or steering committee that has the final say, executive power, rather than whatever the current structure is. But instead of, I mean, if an advisory committee is there and they're just there to advise, right? Not necessarily to tell you what to do. So I guess one way to address these things, actually get the community involvement way before, and then maybe change that advisory council to a scientific steering committee, so that and that's going to be probably made up, can be made up of community members that in that case, they will essentially say up front.
Okay, so thanks. That's
we can discuss it later offline, and that might be a way actually. Anyway.
So, well, let me answer that a little bit. Okay, so there are a few things going on, right? So SIMA is a new project. It's trying to get places, but has been sort of we've been waiting for discussions from our management as to helping us along that path. And so we've been careful about how much community engagement, how much we say it's a done deal versus moving it forward. But we have, remember we had that community workshop a year ago, and we have kept in touch with the organizers of that community workshop and trying to get feedback every now and then from them. But that, I agree, that's not enough, and we don't have a formal government structure, and that's why we're trying to push that forward a little bit more in starting to create a better government structure. But at the same time, we don't want to be duplicating efforts of CESM or WARF or other government structures that are out there. So we want to be complementary, but not duplicative and confusing. So it's kind of, we have to kind of take things in small steps and march forward as things grow and become more common with CIMA. Again, we can talk about it in more detail later, Gokam, but happy to discuss, hear any more comments from Hanli or Bill on that topic.
Thank you, Mary.
Just to add maybe a little bit what Mary said, or just reemphasize, we have tried to move forward with governance, but that really requires NCAR, UCAR, and part of NSF also to be on board with it. And we're kind of waiting on them to give us feedback as to how we're going to move this forward. Our understanding is that it's on their radar, particularly in the director's office right now with the new science advisor on Glenn Romine. But we're still waiting on that.
And a little bit to add to what Mary said too is I agree that the design of, for example, the case experiments, use cases that should happen early on, and actually that's exactly what has been done, or we try to do that in during the vision workshop. Some of the design of the V1 experiment or use cases are as a result of that that discussion.
Okay, thank you.
Other questions or comments? Doesn't look like anyone has their hand raised at the moment. So while people are maybe thinking about questions, if you think of something later after the fact, please feel free to contact any of the CIMA leads. That's myself, Bill, Hanli, or the Missing in Action, Andrew Gettleman. we'll be happy to take that. Or, as we mentioned, Jordan Powers is the project manager for the SE development, but it's, he's a good contact person too. So any of us, if you want to, whoever you feel comfortable talking to. And if you want to, if you're interested in, there's one thing with, waiting until Cima version 1 configurations are ready and released to the community. But if you're really eager to get started and want to get involved, we're happy to make that happen. And again, please contact us and we can, start talking and start figuring out the best ways to involve you all in the Cima model developments.
Okay, I think we are at the top of the hour, 3 o'clock, and maybe we'll end here. Thank you for your participation, and I look forward to work with you in the future on the Cima project.
I see a hand up. What? I saw a hand up.
Oh,
you do?
Your hand?
For a second, it was. It's gone now. Maria, maybe? I don't know.
I was just clapping. Thank you, though.
Oh, okay. Sorry. Yeah.
Thank you.
Yeah, thanks for all the great talks, everyone. We appreciate it.